everyone, my name is Tumnad. In today's video, we are going to be looking at what we call the gastric secretion, mainly on focusing on what we call the gastric phase. If you find it helpful at the end of it, please make sure you like the video, comment down in the comment section, and then subscribe. Let's go ahead and get started, okay? So now you're going to be following these kind of the objectives. We shall look at what we call the overview of the gastric phase. We look at what we call the stimuli, and even also we look at what we call the inhibitory factors. So now, first thing first, we need to understand what is going to be what we call the gastric phase. So now, this is going to be one of the most important phase of gastric secretion, during which there is going to be production of what we call the gastric juice, which is going to be accounting for 2/3 of the gastric juice within the stomach, okay? Something important that the juice which is going to be secreted during this phase is going to be accounting for 2/3 of the gastric juice within the stomach, okay? And during this phase, there is food within the stomach, okay? There is food inside. There is food inside what we call the stomach, okay? In the cephalic phase, there was no food in the stomach, but the stomach was producing the what we call the gastric juice, okay? And then during this phase, you're going to be having the vagus nerve also playing a role in the production of the gastric juice. Besides that, you're also going to be having what we call the hormonal effect, okay? So now you're going to be having what we call vagus nerve. You're going to be having what we call vagus nerve. Vagus nerve. Also, we shall have what we call hormonal. Shall have what we call hormonal effect, okay? So now we have two influences, the vagus nerve and even so what we call the hormonal effect. So now let's go ahead and see the stimuli for what we call the gastric phase. The first one, which is super very important, is that we are going to be having what we call stretch. Now, how is stretch occurring? Now, when you put food into the stomach is going to be having that kind of the stretch to accommodate the food which is coming into the stomach, okay? So now that kind of the stretch, that kind of the distension is super very important, because we have what we call stretch receptors which are on the walls of the stomach. We have these stretch receptors that are having sensory nerves of what we call the vagus nerve. They are going to be taking this kind of the sensation of stretch to the central nervous system, okay? So now you're going to be having stretch receptors. Okay, we're going to be having stretch receptors. These stretch receptors are going to be taking this kind of the sensation to the central nervous system. Okay, now in the central nervous system, we have this kind of the nucleus which we call the dorsal nucleus vagus. Now, it will activate what we call the motor fibers of the vagus nerve. Okay, it will activate the motor fibers of what we call the vagus nerve. So now, this vagus nerve, the efferent fibers, the motor fibers are coming off from the central nervous system, from the brainstem, to come and innervate these different cells on the walls of the stomach. So now, this one is going to be the afferent. This is going to be the afferent fibers of the vagus nerve. And then this one here is going to be the efferent fibers of the vagus nerve. So now we are seeing that it is vagus nerve afferent fibers and vagus nerve efferent fibers. So now this becomes more of a reflex, okay? And this reflex is what we call the vago-vagal reflex, okay? Vago-vagal reflex. So now, what happens is that this kind of the efferent fiber, the motor fibers of the what we call vagus nerve, is going to be releasing a certain type of the molecule. You know how this molecule is called? It's going to be releasing acetylcholine. Now, this cell here is what we call the parietal, cell, okay? And then this one here is what we call the chief, cell. Now, these cells are going to be having receptors for what we call acetylcholine. Now, this one here, let's take this one to be the receptor for what we call acetylcholine, and it's what we call M3 receptors, okay? And even also on the chief cell, we also have what we call M3 receptors. Now, these receptors are going to be now stimulated by what we call acetylcholine. Now, when acetylcholine comes and binds on this receptor, we are calling the M3 receptors on the parietal cell, it will stimulate what we call an increase in intracellular calcium, which will finally stimulate this kind of the proton pump to pump hydrochloric acid into the stomach, okay? Okay, we're going to be having a lot of the protons, of which these protons will later react to what we call the chloride, which will lead into the formation of what we call hydrochloric acid, okay? So the same thing that if acetylcholine comes and binds on the M3 receptors on what we call the chief cell, It will lead again into increased intracellular calcium, which will lead into what we call the fusion of this vesicle containing pepsinogen to fuse with what we call the apical surface of this chief cell, leading into what we call the production of what we call pepsinogen. Okay? So now, for example, acetylcholine comes and binds on the M4 receptors. It will lead into the increase in calcium levels inside the cell, which will lead into the fusion of this kind of the vesicle containing pepsinogen to fuse with this membrane and then powers what we call pepsinogen. Okay, powers what we call pepsinogen. Okay, now when this pepsinogen is going to be now the inactive form of what we call proteolytic enzyme. Now, under the influence of hydrochloric acid, this kind of the pepsinogen is going to get converted into what we call pepsin. Okay, it's going to get converted into what we call pepsin. Now, the influence is going to be what we call hydrochloric acid. Now, the question is, under what pH is this pepsinogen going to get converted into pepsin? Generally, it's going to be close around 1.5 to around 3.5. Okay, to around 3.5. So now, this pH range is super enough to convert pepsinogen into pepsin. However, if the pH goes beyond 3.5, this one is going to be now inhibiting the conversion of pepsinogen into what we call pepsin. Okay? So now, that's generally how the vagal-vagal reflex is going to be leading into what we call gastric juice secretion. Besides that, this is going to be a long reflex, but we also have a short reflex whereby these sensory fibers of the vagus nerve are going to be stimulating what we call the enteric nervous system. We talked about the enteric nervous system having two kind of the two plexuses, the myenteric and even also what we call the submucosal plexus. Now, these kind of the sensory fibers of the vagus nerve are going to be stimulating what we call the submucosal plexus, which can also come over and stimulate this parietal cell and then the chief cells, leading into what we call the production of the gastric juice. Now, that becomes a short reflex, okay? But this vagal-vagal is going to be a long reflex, okay? So now that's generally how this kind of the vagal-vagal reflex is going to be leading into what we call the gastric secretion. So now stretch is very, very important. Some other people may call it what we call distension. Okay, you may find some other people calling it the distension. Okay, so now having seen the stretch, how it is causing the gastric secretions, let's go ahead and see another kind of the stimuli. Okay, so now the second stimuli for gastric secretion under gastric phase is what we call the partially digested proteins. You know, what we call the partially digested proteins, these are going to be what we call the peptones. Okay, we have what we call the peptones. Okay, so whenever I talk about the peptones, I'm meaning those small fragments of what we call the partially digested proteins. They are super very important stimulator for gastric secretion. So now let's go ahead and see how are the peptones going to be stimulating the gastric juice secretion. Now, on the antrum, in the antrum, we have specific cells that are sensitive to what we call the peptones. You see this kind of this cell here. This cell here is what we call the antrum G cell. Okay, so this cell is super sensitive to partially digested proteins. So now, these partially digested proteins, let's say for example, this one is going to be what we call the peptones. Okay, once these peptones come in contact with this kind of the cell we are calling the G cell are going to become activated. And once it becomes activated, it will release a hormone. You know how that hormone is called? It's going to be releasing a hormone called the gastrin. Now, gastrin is going to flow into the blood. Okay? So now it's going to flow into the blood. It moves. You know where it is going? Gastrin has specific receptors on this chief cell and even also what we call the parietal cell. This receptor on the parietal cell for what we call gastrin is what we call CCK2. What happens is that when gastrin comes and binds on this receptor, it's going to be leading into physiological process like an increase in intracellular calcium with the proton pump, allowing the release of what we call the hydrochloric acid. Okay, so now this gastrin can stimulate the CCK2 receptors, which will increase intracellular calcium, leading into activation of this proton pump, leading to the secretion of what we call hydrochloric acid. Besides that, we also have this gastrin can also go and also bind on these specific receptors on what we call the chief cell. This receptor here is what we call the gastrin receptor on the chief cell, which we call CCK1. What's happening is that gastrin can also stimulate this chief cell leading to an increase in intracellular calcium and lead into the fusion of these vesicles containing pepsinogen, and then finally through by exocytosis, pepsinogen is going to be flowing into the influence of what we call hydrochloric acid. Okay, such another a beautiful thing. Okay, let's go ahead and see what are those inhibitory factors of gastric secretion during the gastric phase. Okay, anything that's going to be stimulating what we call sympathetic nervous system, something like fear, stress, and even also what we call depression. Okay, what we call depression. So now these kind of the three events can lead into what we call suppression of what we call the gastric juice. Okay, and then another kind of the powerful inhibitor of gastric secretion, which I want to pay much attention, is going to be this one. This molecule is what we call somatostatin. Okay, now somatostatin is super very important inhibitor of gastric secretion. Let's go ahead and see how somatostatin is going to be inhibiting gastric secretion. Now, within the antrum, we have this specific type of this cell here. This cell here is what we call the D cell. Now, this D cell is going to be stimulated whenever the stomach acidity becomes super very high. He has chemoreceptors that are sensitive to high levels of what we call the protons in the stomach. So now, if we have a lot of the protons in the stomach, these kind of the protons are going to be stimulating this cell we are calling the D cell to release a molecule which we are calling somatostatin. Now, somatostatin can come over here on this G cell and inhibit this kind of the G cell from producing gastrin. By doing that, we shall not have gastrin, which will come to stimulate the parietal cell and even the chief cell. So by doing that, we shall be now inhibiting the production of what we call the gastric secretions. Okay. Besides that, this kind of the somatostatin can move in blood and then it go to this cell. It has specific receptors, or what we call somatostatin receptors in what we call parietal cell. He is going to be inhibiting, okay? He's going to be inhibiting the parietal cell from producing hydrochloric acid. Again, this kind of somatostatin, he has receptors on what we call the chief cell, which we call the somatostatin receptors on the chief cell. He will also come over here and inhibit the chief cell from producing what we call pepsinogen. Okay, so now in that way we are seeing that somatostatin is going to be inhibiting these cells directly, and even besides that, is going to be also inhibiting the G cell from producing what we call gastrin, of which gastrin is a powerful stimulator of these cells to produce their gastric secretions. Okay. So now, having seen that the D cell is producing somatostatin under the influence of too much hydrochloric acid in the stomach, let's go ahead and see some other kind of the stimulus or the inhibitors of this kind of D cells. Okay, we have said that the parietal cell can be stimulated by acetylcholine, binding on what we call the M3 receptors, can be stimulated by what we call gastrin, can also be inhibited by what we call the somatostatin. However, the parietal cell can also be stimulated by another molecule which we call histamine. Histamine is going to be binding on what we call H2 receptors. Okay, now it will also stimulate an increase in intracellular calcium, which can also stimulate this pump, which are calling the proton pump, to release hydrochloric acid. Okay, such another beautiful thing. Okay, then we also have another kind of the molecule, and this molecule is what we call prostaglandin E2. Now, prostaglandin E2 can come over this receptor here. This receptor here is what we call the EP3 receptors. Now, when this prostaglandin binds on the EP3 receptors on what we call the parietal cell, it will inhibit the production of hydrochloric acid by the parietal cell. So now, this kind of the prostaglandins is going to be inhibiting the parietal cell from producing hydrochloric acid. So now, this explains why when someone takes NSAIDs can be predisposed to what we call peptic ulcers. There's again another one important cell that is super very important, powerful stimulator of what we call gastric secretion. This cell here, see this cell here is what we call enterochromaffin-like cell. Now, this enterochromaffin cell can be stimulated and can also be inhibited by different molecules. Now, once somatostatin moves from what we call the D cell, he can come over and he comes and binds on this cell and then inhibit what we call the enterochromaffin from producing a molecule called histamine. So now enterochromaffin-like cell is releasing a molecule called histamine. Okay, so now, but the somatostatin is inhibiting cell from producing histamine. And when that one happens, we are reducing the stimulations of histamine to what we call the parietal cell from producing hydrochloric acid. Such a beautiful thing, okay? And then we also have gastrin coming over through the blood, which can come over on this cell we are calling enterochromaffin cell. And then he binds on specific receptors on the enterochromaffin cell, and he stimulates this enterochromaffin cell produce what we call histamine, of which histamine will come over and then stimulate the parietal cell to produce hydrochloric acid. Okay. Besides that, we also have receptors which we call the M3 receptors. Now, when our vagus nerve releases acetylcholine, he can come over here on this M3 receptor on what we call the enterochromaffin-like cell and stimulate what we call production of histamine, of which histamine can move into the blood and it goes and stimulate what we call the gastric secretion from what we call the parietal cell. Okay, so now this enterochromaffin cell is super very important in production of a molecule called histamine. Okay, so now these H2 receptors on what we call the parietal cell are going to be some of the drugs target. You know, we have drugs which you call the H2 receptor antagonists like ranitidine, cimetidine. Those drugs, they are going to be coming and they block this kind of the receptor such that histamine doesn't bind on this receptor, which will lead into the blockage on what we call stimulation of the parietal cell from producing hydrochloric acid. So now, ranitidine, cimetidine are going to be H2 receptor antagonists blocking this H2 receptor from histamine stimulating the parietal cell, which will block the release of what we call hydrochloric acid. Okay, and then of course this kind of the proton pump is going to be a target of the drugs which you call the proton pump inhibitor, or omeprazole, lansoprazole, esomeprazole. It will block this kind of the proton pump. Once it blocks this proton pump, it will not allow the release of what we call hydrochloric acid. By doing that, we shall be limiting what we call the peptic ulcer disease. Okay, so now these are going to be the targets of what we call these drugs: proton pump inhibitor, H2 receptor antagonist. Okay. Having a quick recap, we said that what we call the gastric phase is going to be accounting for 2/3 of the gastric juice in the stomach. We said that there is food within the stomach. We said that we have what we call the vagus nerve stimulation and even also what we call hormonal effect in the gastric secretion of this phase. We said that the stimuli is going to be the stretch, or what we call the distension when food enters into the stomach. Okay, and then we said that another kind of the stimuli is going to be the partially digested proteins, which we call the peptones. And these peptones, they were stimulating a cell we are calling the G cell to produce what we call gastrin. Gastrin was moving to the blood, which was causing the parietal cell and then the chief cell to produce their secretion. Besides that, the gastrin was also coming on this D cell and inhibiting the D cell from producing a molecule called somatostatin. We said that we also have what we call inhibitory factors, anything that activates the sympathetic nervous system like fear, stress, emotional upset, depression can all inhibit the gastric secretions. We said that the powerful inhibitor is going to be somatostatin, coming from what we call the D cell. The D cell are going to be having chemoreceptors that are going to be stimulated whenever the stomach becomes super much acidic. It will release a molecule called the somatostatin, which can come over on the G cell and inhibit the G cell from producing what we call gastrin. If you inhibit the G cell from producing gastrin, you will not have gastrin being produced to stimulate the chief cell and then the parietal cell to release their secretions. Besides that, somatostatin can overcome into the blood and then goes and block the parietal cell and then the chief cell from producing their kind of the gastric secretions. Okay, so now somatostatin was a powerful inhibitor of gastric secretion during the gastric phase. We said that once this pepsinogen lands into the stomach under the influence of hydrochloric acid on the pH of 1.5 to 3.5, it gets converted into an active proteolytic enzyme which we call the pepsin. Okay. So now, and we said that if the pH goes extensively high and high, for example, up to around 7.2, the pepsin is going to be converted back into pepsinogen, and it will never get converted back into pepsin, even when the pH comes back into 1.5 and then 3.5. Okay? So, Tumnad, I have talked a lot of things, and if you think whatever I've talked is making sense, is adding to you, you are benefiting, please hit the like button, comment down in the comment section, and then subscribe. So now, in the next video, we are going to be now looking on what we call the intestinal phase of gastric secretion. Thank you very much for watching. Tumnad as always. Until we meet next time.